Alrighty, hey, thanks for coming. My name's up there. It'll be easier. I'm half of Dinosaur Polo Club. We're a pretty small outfit. It's just two full timers, so I'm what passes for the technical lead. I should say it's a bit of a small victory as a programmer speaking in the art stream. That's pretty cool. Yes, I was a tech lead on our first and so far only game, Mini Metro. You'd think, having worked on this for upwards of 3 years, I'd be good at describing it at this point, but it's kind of a minimalist subway construction game, so it's based on the style of the London Underground map. You're the players tasked with constructing and maintaining an efficient subway route for a growing city. It almost exclusively uses untextured geometry. The only part of it that isn't in the screenshot are the fonts up on the top right. I am using a bit of a cheat here because there are in the ordinary view of the game, we also have a vignette and other post effects, which of course uses some images. So in this talk, I'll just be going over the how and the why of how we use untextured geometry for almost everything and why we came to the decision that would be a good idea. I'm going to bounce around a handful of topics around that. So the pipelines we use for generating and rendering everything, how we try and do that efficiently, how we make the geometry, how we render it, and the performance. It is a fairly tech-heavy talk. There's nothing too in-depth, but there's a lot more talk about vertices than your average art stream talk. We started development on what would eventually become Mini Metro on Mind the Gap, which was our Ludum Dare entry back in May 2013. So that was hacked together in a weekend in Unity. It was rendered using the Futile framework, which I'll get into in a bit more depth later on, but that was written by Matt Ricks. It's a code-centric framework, so you basically don't use the Unity editor at all. It's not, in hindsight, not the best use of such a cool piece of tech. But for us, it was a really good idea. It was a really easy way to get introduced to the engine. So I've got a shot here from the Unity editor of the game in action. So you can just see what all the geometry we used for that game was. So we've got sprites for all of the stations and the passengers. We've got, and then all of the geometry that we made bespoke for the game, which was the lines and the rail cars. It's just a quick hack with a 32 by 32 white texture with a slight Alfred fringe around the end that we then just stretch, rotate, scale, and recolor for all of those elements. The lines in this game, so the big difference in the rendering between this game and the final game is the lines are always dead straight. So as you can see there, if you're more familiar with the game from this screenshot, you'll see that there are always bends in the lines, whereas here we just always draw a straight line. I always wanted to get that in because as of course this was styled on the London Underground map, and that's such a key indicator of that style. I really wanted to get that in, but seeing it took another sort of 2 or 3 weeks after the game jam to squeeze that in, I'm glad that got left till the end. So we had a really good reception to this. It did pretty well in the game jam, so pretty early on. In fact, even while we were developing this, we had a good feeling for the game, so we decided to continue development into a commercial release that we were always calling the iPad version of the game. So this was an awesome. It's always really good when you're starting a new project from scratch. You've had the chance to do a bit of pre-production through a game jam. I wouldn't recommend thinking that a game jam is your entire pre-production step, but still. So, of course, you've always got all these ideas about how you're going to finally, make this game the perfect way without any bugs or issues. And part of that plan was that we were going to use geometry for everything. So we wouldn't use any images or textures if we could help it. There are a number of reasons why we decided to do that. The first one was, as I said, there is resolution independence. We had really good success with the Game Jam game being playable on a web browser at 800 by 600. So we knew it was going to be displayed on screens that small. Also, of course, we had plans for it to be on an iPad, so 2048 res, and we develop on MacBook Pros, so we really like the idea of having ultra high res as well. And of course, geometry is far easier to scale up. You just have to display it once, and it should display exactly the same on low resolution, high resolution devices. Build size, we had the idea that obviously we had the web build we wanted to make. We wanted to keep that download size as small as we could. We knew about the whole 100 meg over-the-air limit that you have when deploying to Apple devices, and I think it's only just bumped back up to 100 megs for Android. So we thought, well, if we don't ship high-res images with the game, then we just make as much as we can in the game, and that'll help keep that build size down. And, we're both developers, we're not artists. So for us, it just sounded like a fun thing to do. It's always good to give yourself a challenge for a game, something you can use to extend yourself, but not too unmanageable. And it's not as ridiculous as it sounds. Because we're programmers and not artists, it did help to maintain full control of the pipeline in a way we understood. Because we were because we wanted to algorithmically generate all of the art, if we had to make any alterations, it's easier for us as programmers to do it in code rather than open up Photoshop or Illustrator or Inkscape or whatever it was we were going to use to generate the assets and fiddle around with it in there. Also, if there's any animation that we were going to do, it was much easier for us to do it if we have full control of all of the geometry in the code. So once we decided to go ahead with that, how exactly did we make them? So we were still building the game in Unity and Futile. Futile is an engine that's built for sprite rendering, so just a lot of 2D images that you atlas together, and then you just render out these one quad sprites. So not exactly built for what we're focused. Of course, we're generating a lot more geometry. So we extended it to support arbitrary sized meshes, like the ones you've seen there. And then we just built up a simple library of routines to stroke and fill a path. So exactly the same way you do in Illustrator. We build up a path, so you can see that's the red lines there on the examples. And then in this instance, this just shows the stroke routines that we've got. We only do straight paths, so we don't do Bezier splines or anything like that. In hindsight, I'll get onto that a little bit later on. In hindsight, supporting splines would have probably been a really good idea. For the stroke routines, we support inner outer center strokes. We've got a solid brush there on the bottom left, and on the top right there's the center stroke with the dashed brush. Even though we support all these things, the vast majority of strokes we do are just the ordinary stroke, center stroke with a solid brush. If you've ever written a stroke routine, you get into all sorts of issues around edges where the geometry you generate overlaps or intersects, all that kind of thing. And we handle that reasonably well. It's not bulletproof, but it's good enough for what we do. We didn't run into any instances where we completely destroyed it, but you definitely can if you want to. And then next to the fill routines, so I've just got here an example of the 3 fill routines that we supported. So In the bottom left, there's just a simple concave path that we fill. So that's just using a triangle fan, which is the easiest one. And then there's the cross down there, which is a triangle fan still on a midpoint. So that's for simple convex, I was getting them wrong, convex paths. And then the more complicated arrow, which is uses a routine for triangulating complex convex paths. So that's an expensive routine. We only do that if we absolutely have to. And the game doesn't do anything intelligent around figuring out which routine it can use for a path. So when we fill a path, we have to specify, which of those 3 fill routines we employ. So if we're ever doing arbitrary geometry, we always have to specify the complex one. Because it's so slow, like it's fine on that mesh, but we do throw some large paths at it, at which point it's sort of looking for some of the level geometry. It takes upwards of 5 minutes to properly triangulate, so that obviously doesn't run at runtime. So that can make level editing a real pain. Yeah, the vast majority of all the geometry we use in game is done with these fill and stroke routines. There's a few times where it's slightly more efficient for us to sort of hand code the way we make them, but by and large it just runs through that pipeline and then goes through this exciting pipeline, which is how we get from a path to be rendered on the actual screen. So we start off in the top left with the path, so that's where the game generates a path in whatever shape appropriate for the geometry it wants to make. It then does a stroke or fill routine to build up the vertices, so that's just the vertex. At this point, it's just vertex positions and alpha. If we're doing anything fancy with the alpha, and then it indexes that appropriately. It goes through a scaffold, which is just a fancy term for a giant recyclable vertex array. We do it this way before we then compile it into geometry, just to save on allocs, and so we don't have to pre-calculate how big that has to be. That just means we can be a bit slacker when it comes to building the geometry. So that's then compiled to a geo object, which is a fixed size vertex array. And at this point as well, we can then concatenate them together. So if we have a complex shape that's composed of more than one fill or stroke, we can then fill or stroke again, add that to the existing geometry. Then to actually get that into the scene, we make a sprite and then reference that geometry, and then that is then positioned, rotated, colored, alphaed, blah, 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 and positioned somewhere in the scene. This is where futile comes in, and then that goes through all of the sprites in the scene, batches them all appropriately into what it calls a facet render layer. That's when it basically bakes the geodata that we get, positions it correctly by the transform, bakes in the alpha and the color from the sprite onto the geometry, and then generates that into one giant vertex mesh, and then finally copies all that into a Unity mesh, and or it updates that if it can. So if it's retransforming existing sprites. So that is a convoluted pipeline for how we actually get stuff on the screen and end up with this again. So now that I've just described how we actually make all the stuff, I'll just go through the elements of the scene, and just before I go in depth into the issues that each of them has. So we've got, in this shot of the London, we've got the river going through the map. So that's a filled background and a stroked outline from the same path. So that's sort of the most traditional asset we've got. Then there are the icons on the left, the middle left. So that's a filled path over a filled circle. Then we've got the stations. Again, that's a filled background and a stroked outline. And then the most elementary pieces we've got are the passengers and the trains. So those are the little circles and squares and triangles that are by the big stations. They're a simple fill over a shape. And then the lines. The lines are the most interesting part of Mini Metro. It's the bit that they look the simplest in some ways. They're the most difficult in others, but they are really what makes the game it is. So first of all, I'm just going to go into the obstacles. Well, what we call the rivers and whatnot. So as I said before, this has the most ordinary pipeline of any asset we've got. We use Inkscape as our editor if we have one. So each steady file we have is an SVG file that we open up in Inkscape. It has a whole bunch of other information about it that's used by the game, but as far as this is concerned, it's just the path for the river that we're concerned about. So we have one or more paths that we use for the obstacles. We have an exporter that reads that SVG file and pulls that path out and dumps it into JSON, into a series of points. This is kind of gross. Yeah, so that's fine for what the Thames does, because that's fairly small. It's actually less complicated than what's seen here, because the path that we export doesn't actually have the smooth edges. We smooth all those edges in game. So yeah, so it's fine for geometry that's abstract, for a map that's abstract. But if we look at, this is an example. So on the left we've got the little London Underground map. So the actual London Underground map from the and then on the right is the New York map. So a key part of the game is this connection that you have. If you understand, if you travel on the London Underground, we want to make the London Underground map in the game feel sort of as home to you as it can. So we really try to preserve as much as we can from that map in the game. And that's great when it's an abstract map like that one. But the New York map is obviously not as abstract as the London map. So we had to preserve that outline as much as we could. So all of a sudden we've got what was in London, which the whole pipeline was designed for, has maybe 200 points on it. The New York map, I actually don't know how many points the New York map has on it, but it's a lot. Interestingly enough, the New York map used to be an abstract map. Back in the 50s, I believe it was originally rendered in the same style as the London Underground map. But people hated it for one reason or another. I guess the connection to the geography that people had wasn't as strong when it was an abstract map. So they turned it into this thing eventually, which is one of the more reviled pieces of design in the world. I think it's instead of simply showing the abstract connection between all the stops, it tries to. I mean, you can see there's a street map on there. It shows you where all of where the Statue of Liberty is and where all the interesting tourist attractions are. It's a very confused map, which doesn't make our job any easier. Also, the way we design the lines is obviously based on the London Underground map, and then when it is a bit jarring in our game when you're rendering the 45-degree angle lines of the London Underground map on top of the accurate, relatively topographically accurate New York map. But unfortunately, there was no way we were going to build in spline support for editing lines as well. And so this is what a more complicated map looks like in the Unity editor. So this is the Osaka map. So this is the most complicated map we've got in the game. So yeah, as I was saying, the pipeline worked well for the London Underground map, which is what we designed the whole pipeline around, and then any other maps in that style, the Melbourne map and the Hong Kong map, for example, work really well as well. But unfortunately, ones like New York, St. Petersburg, Osaka, etc., don't work as well. So this is the map that takes about 5 minutes to generate when we edit it. So what we do is we have to import them off in an offline build, compile it all out. Once it's all been converted to a mesh, dump that out, and that's what the retail builds will import instead. So this didn't really get us the benefits we were after. Seeing we have to save, even though we've got this dynamic data that we make the mesh from at runtime, we had to go with a more traditional approach and save an asset out, import the asset at runtime. It also doesn't handle curves very well because we don't support splines in the paths that we make in Inkscape. We have to plot all the points ourselves. So if we want to have a smooth edge, then we've got to plot all of those points. That makes it very time intensive and geometry intensive, of course, if we want to make a smooth edge around a long, shallow bend. And again, this breaks with resolution independence, what we're aiming for. On a low-res screen, it doesn't matter so much if you only have a few points, but if you view that same piece of geometry on a really high-res screen, all of a sudden you can see the facets in Manhattan, for example. We don't support subtraction in our paths, so all of the islands you can see there in Osaka are actually separate paths that we fill in the background and display in the same color as the background, and then overlay that on top. So that's the only way we got around that. So moving off obstacles onto icons, I just realized I'm just going over all of the horrible issues that we've got. It actually works well, but yeah, probably should just put a disclaimer there. So the icons just have the most ridiculous convoluted pipeline of any of our assets. It gets so backwards. Our artist sends us an image of the icon he wants, so he'll paint that up in Illustrator or something, and I think he uses Illustrator. I don't know. Then he will send us the image, and we then import it into Inkscape, and then I trace around it. So I'm probably recreating his work. It sounds even more ridiculous when I'm standing up here in front of people explaining it. We flatten the curves, make sure it's the right part, and make sure it's the right way. We then add an extra geometry for holes if we have, because we can't do subtractions. And then we run a Python script which reads the SVG and generates C# code that we copy and paste into our file somewhere that builds the path up, and then we complete that C# code by saying to fill or stroke in the appropriate way. This really does show how we were cutting off a nose. No, that's the wrong analogy. We were just jumping through hoops just to make sure we didn't have any images in the game, or as few images as we could. It really was completely ass backwards. But so here, this is what the output is. So on the left, you can see this is the some C# code that the exporters generated that we've stuck in. You see all of the hard-coded floats and whatnot in there for all of the XY positions for the path. We have, as you can see, if you can look at the outline on the right side of that Sublime text screen, you can see all of the different meshes we have. And then on the right is what comes out of it. So that's a carriage icon with one filled geometry and then two windows. rendering the windows like that doesn't work as well as it does for the background, because when we're displaying the background and we show that it's not overlaid on top of anything, whereas these icons can be overlaid on top of certain things. So it's not ideal that we have to pick one color to render the windows as. Yeah, so this is exactly what we ended up with was exactly what we wanted to avoid, which was this cumbersome, error-prone pipeline that we hate and our artist hates, and like he's sometimes unsure as to what restrictions he has and how exactly he gets images to us, and then it's that standard artist programmer butting heads when he hates how long it takes for an alteration that he makes to get in the game, and we get annoyed every time he wants to make a slight revision on the assets. But moving right along to lines. Yay, lines. Lines are like the rock stars of the game. These are the meat and potatoes. It's the player's primary method of interaction. It's like almost all of the interaction that players have in the game is with these. So they really needed to feel good. I know it's weird talking in emotional terms about geometry, but just to get them to feel and behave and feel fun to pull and animate was really an important part of making people sort of engage with the game, and being tactile, like that's a verb that people, that's a noun people use to describe the game quite a lot, and so it was really important for us to get that right. So so each line is made up of links. So each link is any part of the line that connects two stations. So because it's all designed on the London Underground map, all the lines are either straight, so straight up and down, straight left and right, or on a 45-degree angle, or in this case they're made up of a straight line and a 45-degree line connected by a bend. Oops. And they're always built to nest together, so when they run, so up to 3 lines can run in a parallel configuration like that between 2 stations, and they nest elegantly as they go around the bend, as you can see there. And then these are made a lot. This is generated more often than any other geometry in the game. When players are building a line, pretty much every frame will be destroying the old geometry, creating new ones. So almost all of the heartache and pain in the game was made by these. So the most complicated bit about lines is not the lines; it's not the connections between the stations, but where 2 links meet at a station. The problem we have is the beginning and the end of the links that go into the same station, each of them could be coming in any one of 3 positions on any one of 8 directions, and then to try and connect those 2 elegantly turned out to be quite a difficult endeavour. It's not easy to solve in a generic way, just because we're going everywhere from a straight line to 2 lines that are coming in are just offset, to hairpin bends, to 45-degree bends. So it ends up being something over 500 different permutations of how that works. And our artist came up with all of these illustrations and a whole bunch more of exploring all the different possibilities we could use to connect them underneath the stations. And he didn't do all 500 or anything, but he definitely came up with ideas that we could extrapolate out to solve all of them. And unfortunately, I whipped up a temporary solution. So this diagram here, up in where that circle is, there's meant to be a station there. I've just removed that station so you can see what happens underneath when we connect them up. So instead of bespoke junctions, we just smooth them out with splines. So both the incoming and outgoing lines, if they don't meet at the same point, we cut them off a fixed distance from the station, from the connection. So that's what that black circle indicates. That's the radius around the station where we chop them. We then just build a spline, and you can see on the red line at the top, that black line, those 3 black lines, that's a 4-point spline that we use to connect the 2 ends. And then we just use that path, so then we flatten that spline out to a series of points, and then we strike and where we do a stroke and add those strokes onto the lines, and they also use that to generate the path that the trains go on as they go over the line. It only covers 90-degree and 45-degree and straight ahead bends. Hairpins and acutes, we just can't connect them when they go that steep bend, so we just stop the car, jump the tracks, and then start them again. It's far from ideal. As you can see, there's no reason that 45-degree bend at the station and intersection shouldn't look the same as the other 45-degree bends. So it does generate comparatively ugly connections. So here's a more involved example. This is when the platforms switch, so we go from the outside to the inside connection. And then we just pop the station on, and it hides a multitude of sins. I mean, it looks nowhere near as elegant as it should, but again, this is one of those times when good enough is the enemy of perfect. So, and that temporary solution quickly became permanent. It's just one of those cases where it's hard to justify spending the time on fixing something that's already working, which was a bit of a shame. And that segues really well into anti-aliasing. We knew that anti-aliasing was going to be an issue with the game, and we knew we had to have anti-aliasing. It's just what you have to do if you don't have anything to hide those edges. Early builds we had, which when we didn't have an anti-aliasing, any anti-aliasing solution, were pretty horrible. They flickered all over the place. Even the straight lines, the square and there and the straight line, they look fine here, but one of the key aspects of the game is it slowly zooms out. The game slowly zooms out and pans, and if you're trying to zoom out a line that doesn't have any anti-aliasing on it, it warps and shimmers as it slowly shrinks, which is just looked diabolical. So we played around with a few options. So I was trying to research pixel coverage anti-aliasing options, and we did just try flicking on hardware anti-aliasing. Hardware anti-aliasing looked okay. Even on the PC though, the job it did wasn't fantastic. And if you've ever looked, it's not as simple as when I was doing this 5 or 10 years ago, when it was all just MSAA. There's all sorts of funky algorithms now, and it just lost the clean look that sort of defines the game. And we knew, of course, that putting that onto a phone, especially a low-powered phone, and any anti-aliasing is a stretch, especially on the old iPad 3. So we knew we had the edge information, which is a lot more than almost everyone else has when they're trying to solve this issue, and we knew we only render it from one angle, so how hard could it be, right? So in the end, we used an alpha fringe. Well, I don't know what its official term is, but that's what we call it in game. So pretty much every geometry, all geometry with a few exceptions where we don't display the edge, uses the same technique. So what we basically do is, once we've stroked or filled, we then use the edge information we have to generate an extra set of faces that fit around the edge. So you can see the inside vertices of the quads, so the ones in the border between the pink geometry and the black geometry, those are the inside edges of the the fringe, and they're all set to the same position as the edge geometry, and their alpha is set to 1. And then we have the external edges of the geometry, which are the ones in the bright pink, which are set to alpha 0. And their position is also set to the same as the external fringe, and then we have a vector that points away from the edge, and then we extrude, in a vertex shader, we extrude the fringe so that that quad is always half a pixel on the screen. And that gives us really smooth edges. It's funny, when I was putting this together, I noticed the triangle on the edge in the top left looks a little odd compared to all the other edges, so I have no idea what's going wrong with that algorithm, but all works fine. So this is what we end up with, is where we had that, we now have this. And once I implemented that, just on a whim, just to see if it worked, I was like, oh, it actually looks fine, and looked better than any of the hardware anti-aliasing we switched on. And the great benefit of it is it was all implemented in C#. It worked cross platform. We didn't need to worry about any specific platform-specific code or hardware issues or feature set that would be supported on one device and not on the other. It's simple, it's reliable, it has the same issues that the stroke routines we have do, where if it's around tight edges, it'll overlap, but in general, because it's alphaing out, it isn't really a huge issue. It's quick. It's quick when we re-implemented it in C. I think the original PC build shipped with it in C#, but for phones we pushed it out to C, but it's a pretty easy routine to do that with. It is a bit of a pain when you start pushing code out to C, because you've then got to recompile it for every platform every time you alter it, and so recompile it for PC, Mac, Linux, Android. But we actually we've pushed out heaps of code since then to C. So the downsides, though, as I said, it's not good at tight edges. All of a sudden we had to blend everything. It's great when you've got opaque geometry and you can just not have to worry about render order and the performance hit you get with alpha'd geometry. So now absolutely everything had to be alpha'd. And the main downside was it was so geometry heavy. I mean, as you can see here, we've tripled the geometry. We've once you include the end caps, it's over 3 times the faces to display. And that really meant the introduction of all of that extra geometry really meant we had to rethink how we displayed things. Because the way Futile works is it obsessively batches everything. So pretty much all of the game geometry when we were displaying this, when we introduced anti-aliasing, was all batched into one thing, and then that finally took us over the 65K indices that we were trying to put into one batch in one game. When we did push that update up, I think that was when before we were on Steam, so it was only the web build. But yeah, we put that up, and I hadn't actually run a game to the fullest of conclusions. So, and what happened when people were playing it and they broke 65,000 vertices is those extra bits just didn't show up in the game. So all of a sudden there were stations that were disappearing. There were all sorts of bits that they weren't being displayed. So yeah, it's just another cautionary tale, and actually play your game before you push it up to a build, which we still don't do, but anyway. So just a bit more into Futile now that we actually had to start work on optimizing this stuff. As I said before, it's a code-centric, two-dimensional sprite framework developed by Matt Ricks, which he open sourced. I think he used it for Disco Zoo, but now he does his own. It hasn't been in development since 2011 or 12 or something like that. Yeah, the rationale for us to use this was, as I said before, we were both programmers, didn't have any experience in the tool, so this was a great way for us to get stuck in without having to learn how Unity actually works. It was great for us to make a couple of early prototypes and to develop that game, develop the prototype in, but probably shouldn't have stuck with it for this game. In hindsight, we should have either gone with a completely bespoke solution or used Unity properly. But hey, so yeah, it's really good at Atlas sprites. That's what it's designed for, and that's what it's excellent at. It's really obsessive about minimizing batches, so it's almost pathological at batching. And it does that, unfortunately, by transforming pretty much every vertex on this CPU and then doing uploads. So any transform change will cause that mesh to be retransformed, put into the vertex buffer. That entire vertex buffer has to then be re-uploaded. So again, because it's designed for low vertex environments with sprites, it's not that big a deal. And it began not being a big deal for us, but as we added more and more things into our scene, it became more and more of an issue. So this was the process we took to make it workable for us. I am simplifying the process here. I'm just going to go over 2 versions of the renderer that we'd used, as if those were the only 2, but obviously we were experimenting and playing around a lot. So the first thing we did was break up the connection Fetal has between the render order and the hierarchy order, just to make it easier. So, for example, fonts, which use images, and all of the rest of the geometry, which did not use images, didn't break batches. We used the camera. We changed so it wasn't transforming all of the geometry every frame, as long as the only thing that was moving was the camera. That saved us a ton, because as soon as the zoom begins on the game and it zooms out, which is after about 30 seconds of play, as soon as that started, every single vertex in the game had to be transformed at once. It was that's when it just started getting ridiculous. And the most important thing we did, which I haven't put out here, is made it so it supports breaking 50,000 vertices in a batch. And that ended up with us having about a dozen batches in the scene, and that was what I'm pretty sure that's what we shipped with on Steam. For the first build we stuck up on Steam. So that was great. Desktop, you can get away with anything. However, so when we started doing mobile development, that wasn't so great. It's kind of difficult to judge when we got the performance gains on this, because we were using Unity 5.1, 5.0 or something, which is when they first introduced IALTIS EPP, and that first implementation of IALTIS EPP was horrendously slow. So when we got back to mobile on Unity 5.3, it was a lot speedier. But we still had... So this is when we realized that 20 batches was a bit ridiculously low. Like, that was hard. Like, you're always told to keep the batch count low, but keeping the batch count that low at the expense of all this other stuff you're doing is not really worthwhile. So we figured, why not relax the limit on batching, relax the obsession on batching, just to not do so many transforms. So we basically went back to the way normal rendering works, instead of trying to batch everything, and all of the passenger stations, trains, clocks, icons, anything that was static geometry, we just rendered that as its own batch. And if they transformed, then we just moved the mesh like a normal game does. And that worked well, funnily enough. It does go to a single batch each, of course, so in the case of the passengers, the batch count has shot up, because each passenger, and there can be a lot of passengers, are all displaying in their own batch, which isn't great. I'll get onto how we're working on that. All bits of dynamic geometry still remain batched, and so now the batch count is now several hundred, so it's more than it could be. Vertex uploads are relatively low, and this is what we shipped with on mobile. Only last week, by the way, available on the App Store and everything else now, so you should, yep. check that out. So these are the performance issues we're still having. So this is a Unity Profiler example from a simple scene at the start of the game when the game's paused and someone is building a line. So you can see there I've got, from the iPad Mini and the iPhone 6, what's happening under the hood when you're actually displaying a line. So the hit on the CPU there is both the mesh generation and then uploading the vertex buffer every frame. You can see it's not so bad on the iPhone 6. I assume, because I don't know exactly what's going on under the hood, I assume this is because the iPhone 6 has, Unity has access to the unified memory architecture on the phone, so vertex uploads aren't as bad as they are on the 5 minutes. Are you serious? Oh my goodness. It's a lot more efficient. But still, you can see on the iPad Mini, it's pretty bad. That's just us doing one piece of geometry in a frame. And this is what the game can look like at the end game. So this is where all of those batches come from, seeing all of those passengers as individual batches. And yes, far too many passengers. So this is what the performance we're getting on mobile is. So we're having upwards of 300 batches. We get either around about 60 or 30 FPS. We don't guarantee any of those. Unfortunately, in certain situations they dip below it. But the main thing we've learned really is both, batches and uploads are bad. You want to keep them both down, but don't do what we did and throw one way out at the expense of the other, and that we've sort of been seesawing between those two. So the next step for us to improve performance, this is something I've been working on a branch. It's working fine in theory, but there are a few little issues to work out. So the main reason is just we recognize that the line geometry is all just a 45-degree bend with one straight bit out one end and one straight bit out the other end. Using a similar technique to how we rendered the alpha fringe, we can just parameterize the whole thing and have constants in the vertex shader that we can use to extrude out both the lines left and right and also the width of the mesh as well. So when we implement this, it's just it is the best of all worlds. It does mean we have one batch per line, per ink, but it does mean that we don't allocate anything, we don't upload anything when you're building lines. The second thing is batching, but with static meshes. So this is a pretty much identical technique for how skinned meshes are displayed. So we use a palette of transform matrices, but you only have a single bone index per vertex. So we just group together a whole bunch of identical passenger meshes in one array, and we should be able to group roughly 100 passengers into one vertex array, and then just animate each of them by uploading the 200 odd uniforms into the vertex shader. And then the next one is using the static link junctions that our artists so carefully designed and I completely ignored. This is basically a win on all fronts. It looks better, it reduces dynamic geometry, no more runtime mesh generation or allocation. It looks a lot better. I just need to get off my butt and implement it. I've started on that on a different branch. So in the end, how did all of this weigh up against against the reasons we wanted to go with a mesh heavy approach? The resolution independence, we pretty much got what we're after. It looks as good as it can for what we're trying to display on everything from 800 by 600 web builds to iPad Pro. Again, the only thing is just generating curves, supporting curves from the ground up would have been awesome for us. Any curves we generate in game, we do generate at a high resolution. We scale up the resolution we evaluate them at, but anything we generate from Inkscape, for example, we don't. Build size was a bit of a wash. I don't think we gained anything here really because the amount of texture data we saved probably wasn't worth anything, really. I mean, it was all a bunch of icons and would be realistically what we could save, and we could fit that onto one reasonably sized image, and that would be fine on all resolutions. And ironically enough, because we have to cache the geometry for the cities, that takes up all of the space we would have saved any other way. And as for the challenge, to be honest, I mean, a lot of the way the lines are displayed, and that's where almost all of the difficulty for us came. There was no real other option for us to do that anyway. Did learn that the desktop makes you weak, and modern GPUs and CPUs have so much redundancy. When you're trying to make a game as straightforward as this, that as long as you're not doing something horrendously inefficient, you get away with anything. But embedded systems just don't have that same slack, and you do things slightly wrong, and they make you pay for it. Plus, of course, if you've got not all 60 frames per second games are built the same. You know, if, you could have a 60 FPS game that burns through your battery in half an hour. So it's always any performance gains you can get there are good. But realistically, what we should have done in hindsight is fully explored the pipelines that we had. You know, we thought we did proper pre-production, but that pre-production was based on based on one map, you know, rather than exploring all of the issues we had to get through. And that's the end of the line. I can't say that. That's it. Thank you. Do we have time for any questions? A little bit. Does anyone have anything they want to ask? Yep.
Is there a particular reason that you use both Inkscape and Illustrator? Is it purely so you have more control over the assets generated, or is it...
We used Inkscape. I mean, our artist, I don't know what our artist uses. It might be Illustrator. I don't know. So but us and our side, we just use Inkscape. Anyone else? Yep.
What's your favourite mini metro map?
London's what I stare at every time. That's just the default thing, is starting up in London. We have to test something in game. So I don't want to see that map ever again in my life. So probably anyone but that one. Yeah.
If you had to do it again, would you do sprites more for the other icons?
Possibly. Yes, even now it's hard for me to give up on geometry. But yeah, I probably would, actually. Yeah. Cool. Thank you very much.
Thank you.